Okay, think about this. If you want to change an electron's path, you have to hit it with something, right? A force, like an electric or a magnetic field. But what if you could mess with an electron's behavior by doing literally nothing to it? Yeah, let's get into it. This is going to be a weird one. And no, that is not an exaggeration. That quote right there is the key to a discovery that completely flips our understanding of empty space. Spoiler alert, it's not empty at all. It makes you wonder, right? What's actually real? Is it the forces we can see and measure, or is it some invisible landscape that's pulling all the strings?
So this is the big question. This is the whole puzzle. How in the world can you change what an electron does when there is zero force on it? I mean, it sounds like a trick question, right? It sounds like it violates everything we learned in high school physics. But it's not a trick. It's a deeply weird and very real part of how our universe actually works.
So how is this even possible? Well, the whole story really kicks off back in the 1950s. It started with just a thought experiment, one that would basically tear the physics community in two and start a fight that honestly is still going on today. Okay, so this idea is called the Aharonov-Bohm effect, and when it first came out, it was just completely nuts. The prediction was this: you could have a magnetic field completely locked up in a box over here, and an electron could fly by way over there in a place with absolutely no magnetic field, and somehow that electron would know the magnet was there. That's just not supposed to happen. It breaks all the rules. But here's where the story takes a crazy turn. The key to solving this quantum puzzle? Well, it was found by accident, 100 years earlier, by mathematicians who were trying to solve a completely different problem, a problem that was famously impossible. So you've got the two-body problem, think Earth and the Sun. Newton knocked that out of the park 300 years ago. The orbits are clean, they're predictable, beautiful. But then you add just one more body, and suddenly it's a disaster. We're talking a chaotic mess of force vectors, arrows just pointing everywhere. It was a complete mathematical nightmare. So what do? How do you solve that mess? For over a century, the smartest people on the planet were just stuck. They were trapped thinking about forces as these little arrows pushing and pulling. Turns out the problem wasn't the physics. The problem was the way they were thinking about the physics. They needed a totally new approach, something that just threw out the vectors altogether. And that's where this guy, Joseph Louis Lagrange, comes in. We're talking the 1770s now. He came up with this brilliant workaround, this mathematical trick that would end up changing everything. So instead of all those messy arrows, Lagrange said, let's just make a map. For every single point in space, he just assigned a number, a simple number, a scalar, which he called potential. The best way to picture it is like a topographical map of a landscape. A huge object like the sun creates this deep valley or well in the map. No arrows, no directions, just numbers representing the height at every spot. Okay, so here's the clever part. You've got your map, right? Now, if you want to know the force at any point, you just look for the steepest way downhill from that point. That's it. The steepness of that slope, that tells you the strength of the force, and the direction of the slope tells you the direction of the force. You get the exact same answer as the old, messy vector way, but the math is 1,000 times easier. But, and this is super important, for almost 200 years, everyone, including Lagrange himself, thought this was just a tool, a clever shortcut. Nobody, and I mean nobody, thought these potentials were actually real. They were just a useful mathematical fiction, kind of like a ghost in the machine. And that leads to the big, nagging question that just sat there for decades. If this whole potential thing is just a made-up mathematical convenience, how could it ever have a real physical impact on the world? For just about every physicist, the answer was a hard no. And their reasoning seemed bulletproof. Think about it. You can take that entire potential map and just lift the whole thing up, raise every single point by 10 or by 1,000,000. You know what changes? Nothing. The slopes are all still exactly the same, and since the slopes are the forces, the physics doesn't change. Because the actual number for the potential seemed totally arbitrary, it couldn't be real. It had to be just a trick. But you know how this goes. That assumption, held for nearly 2 centuries, was about to get completely blown up. And it was all thanks to 2 physicists who were kind of on the outs with the establishment, who saw something in quantum mechanics that everybody else had missed. So, let's talk about David Bohm. This guy was brilliant, absolutely top tier, but his career got totally sidetracked by Cold War paranoia. He was banned from the Manhattan Project, forced out of Princeton, basically became an academic outcast. So he ends up working in exile with his student Yakir Aharonov, and freed from the mainstream, they start tackling old problems with a fresh and pretty radical perspective. And they notice something big. When you look at the Schrödinger equation, which is like the master key to all of quantum mechanics, what's in there? It's the potential, not the field. And Aharonov has this incredible aha moment. He thinks, wait a minute, what if this isn't just a shortcut? What if on the quantum level, the potential is the thing that's actually real? So they came up with an experiment to put it to the test, a definitive showdown. The idea was simple. You shoot two beams of electrons around a magnet that's perfectly shielded, so no magnetic field can escape. If the old way of thinking is right, and only fields are real, nothing should happen to the electrons. The pattern they make when they meet again shouldn't change at all. But if the potential is real, then that pattern has to shift, even though the electrons never felt a single bit of force. So the first attempt was in 1960, and it actually seemed to show a shift. But people immediately pointed out flaws, saying the experiment wasn't clean enough, and for the next couple of decades, that's how it went. More experiments, more debate, but nothing conclusive. The argument just went back and forth. That is until 1986. That's when a physicist named Akira Tonomura finally designed the perfect, undeniable experiment. What he did was genius. He used this tiny, perfectly shielded donut-shaped magnet. There was literally no way any magnetic field could leak out. And when he sent the electrons around it, the interference pattern shifted. It shifted. The effect was real. There was absolutely no doubt. Something invisible was reaching out from inside that shielded magnet and touching the electrons in a region of space where there should have been nothing. But here's the thing. Proving the effect was real didn't solve the mystery. In fact, it just made things weirder. It opened up a brand new debate, an even deeper one. What in the world does this actually mean about reality itself? So now physicists are basically forced to pick between two equally bizarre options. In Camp 1, you have people like Bohm and even the legendary Richard Feynman, who said, okay, I guess potentials are real. That old mathematical trick is actually a fundamental piece of the universe. Then you have Camp 2, which argues that, no, fields are real, but they can act at a distance, non-locally. It's like a spooky action at a distance. Imagine a ghost in the basement flipping a light switch on the second floor. The cause and the effect are in two different places. And get this, Yakir Aharonov himself, one of the guys who came up with the whole thing, he eventually switched sides and joined the non-local camp. He now says, and this quote is just amazing, that the electron can feel a field that isn't where the electron is. Just think about that for a second. It's an idea that just fundamentally messes with our concept of space and reality. And this story is still being written. Just in 2022, researchers at Stanford managed to confirm a gravitational version of this exact same effect, which is mind-blowing. It means this isn't just some weird quirk of electromagnetism. It applies to gravity too, to the actual fabric of space-time itself. So, where does that leave us? Well, with one final, absolutely reality-shattering question. We're always taught about the fundamental forces of the universe, right? But what if they aren't fundamental at all? What if the forces we see and feel are just symptoms, the downstream effects, the slopes on the map of a much deeper, much stranger, and completely invisible reality that's actually running the whole show?